And then now re tlo discuss about Newton's laws. Re tlo discuss about Newton's first law, second and third. So re thome ka this one, Newton's first law. This law an object at rest will remain at rest. An object in motion will continue in a state of motion unless acted upon by an unbalanced force. Actually, this law is made up of two parts. The first part an object at rest will remain at rest. And then the second part an object in motion will continue in a state of motion unless acted upon by an unbalanced force. So first, this first part. When it says rest, something is at rest, but is not moving, is stationary. So now let's say this is a desk, and then we have a book on this desk, and then suddenly you leave. Expect this book it la dula on this desk forever and ever. This book it on this desk, there was a certain force applied, because a force is a push or pull. So that is why it says an object at rest will remain at rest, because this book on this desk is at rest. So re expect it la dula here forever and ever unless acted upon by an unbalanced force. Let's understand an unbalanced force. Any object is stationary, the forces are balanced. For the reason this object ga e godimo ebile ga e fase, these forces are balanced. The upward and the downward forces are balanced. And then for the fact this object are to the left or to the right, these forces are balanced. But the moment this object is a mover, now the forces are no longer balanced. So that is why it says unless acted upon by an unbalanced force. So that is this first part. And then now let's see this second part. This second part an object in motion will continue in a state of motion. Let's first understand this. Motion re no bolela ka any moving object. Object the mover is in motion. So it says an object is in motion, in motion unless we value a certain force stopa that object. An object on the air, expect this object is on the air forever and ever. We are fast. But we are fast only a certain force oppose. And then in this case, that force it laba a force of gravity, because force of gravity the objects declare downwards. So this is this part. Another way I understand in this way. Let's say mornally two surfaces, and then let's say this one is a smooth surface, and then let's say this is a rough surface. Two objects. Let's say uja a tennis ball where we are here, and then where we are here, and then suddenly you roll these objects. Rolla this object, and then warola this object. The truth is this one on the smooth surface but this one on the rough surface yo kapela. This is because on this surface there is high friction. Remember, a friction opposes the direction of motion. There is no friction, this object forever and ever. But due to friction, this object at some point will stop. So that is why for this one on the smooth surface it can stop early. This is because on the smooth surface the friction is less, but on the rough the friction is high. So that is why this one here yama early, but this one here yama later. Is due to friction. Object on somewhere, and then this object roller expect or roll forever and ever, but for the reason you're a stopper there is a friction, and then there's about friction always opposes the direction of motion. So that's all about this Newton's first law. And then morally inertia, actually inertia in the property Newton's first law. This inertia is the tendency of an object to resist its state of rest or motion. Actually, this is based on Newton's first law. Let's say, for example, you are in a car, and then this car is a velocity 120 meters per second. You are in this car, and then this car is a velocity 120 meters per second. The same velocity, and then this car is suddenly a stopper. What will happen o ka se stop immediately or thoma ka ya pele before o tlo stop? Here, based on this inertia, you are resisting the state of rest. This car is stopper, but when o gana stop, what are you doing? We are forward first before you're going to stop. I apply this Newton's first law. An object at rest will remain at rest. An object in motion will continue in a state of motion. This is because you were already in motion, and then because this object is stopper, you must continue in a state of motion before it stop, because now the force applied. So key this part here, the tendency of an object to resist its state of rest or motion. And then another example bus, and then it happens this bus is stationary, is at rest, right? We emelage, and then this bus ya move. What will happen o thoma pele wa boela morago? Wena o gana o ya pele because you were at rest. You want to remain at rest because an object at rest will remain at rest. So this can be applied in a real life situation, and then already applied. This is based on Newton's first law and the inertia. The importance of wearing the seat belts. What we know a person in a moving vehicle travels at the same velocity as the vehicle. Already get halosage. You are in a car and then you travel at a velocity 120 meters per second. The same velocity. And then if the vehicle suddenly stops, the person continues to travel at the same velocity due to the inertia. Remember, inertia is the tendency of an object to resist its state of rest or motion. Therefore, a safety belt keeps a person in his seat and prevents him from crashing through the windscreen and being thrown from the vehicle. Because this car let's say during the accident, because it's a mayaga velocity 120 and then we're not a mayaga 120, this car when automobile wire bill. So that is why the chances go o faster, and then that is where the injury. So that's all about the Newton's first law and the inertia. Those are some of the important questions they might be asked in the exam, and then banyaga will apply a certain Newton's law, and then we know Newton's first law. So that's all about this law. Let's see this one. Newton's second law. When a net force is applied to an object of a certain mass, the object will accelerate in the direction of the net force. The acceleration is directly proportional to the net force and inversely proportional to the mass. Actually, for this law, re shumisha this formula. F net equal to MA. And then from there, ke dira A subject of the formula. Ke divide both sides ka M. So re la gore A yo lekana le F net over M. This A ke acceleration, and then this M ke mass, and then this F net in re ka force. So let's understand this first part when a net force is applied to an object of a certain mass, the object will accelerate in the direction of the net force. Let's say more an object a certain mass, and then let's say we apply a force, we push this object to the right. Based on this first part, the object will accelerate in the direction of the net force. O apply a force is to the right on this object, leave this object in the direction of the force. So this object to the right. O apply a force on this object, your force is to the left. I expect this object here to the left, but it really makes sense. And then let's look at this second part. The acceleration is directly proportional to the net force. First, let's understand directly proportional. Let's say this is A and this is B. When you are saying A is directly proportional to B, A ya increase, it means le B it will increase. Re decrease A, le B it will decrease. So this is what we mean by the directly proportional. So whatever re dira mo A, le mo B yo direga. So whatever re dira mo B, re le mo A ya go direga. So that's what we mean by the directly proportional. And then when we are saying inversely proportional, ke opposite. Ge ile gore ke increase A, re la gore B yo decrease. Ge ile gore ke decrease B, A ya go increase. They are inversely proportional. So now I level this part the acceleration is directly proportional to the net force. Acceleration increase, net force increase. So let's see here. Let's say these two situations. Let's say a tennis ball is on a frictional surface. Let's say this object is the same mass, and then now we apply a force or this object, and then we apply a force here 50 newtons, and then on this one we apply a force here 10 newtons. Let's see in terms of acceleration. This object compare these objects. This one because ke apply a greater force, this object you the high speed, and then this one because force again speed sa gona ska selekane le sa this one. So here we kgona bona the greater the force, the greater the acceleration, and then the smaller the force, the smaller the acceleration. So this part the acceleration is directly proportional to the net force. If the force is greater, the acceleration will be greater, because it really makes sense. You push a car a very small force, and then a push the same car a very high force. Those cars at the same velocity. The greater the force, the greater the acceleration, and then the smaller the force, the smaller the acceleration. So that is what is meant by the directly proportional. This formula, what you should know this value is directly proportional to this one, and then this one is inversely proportional to the denominator. The higher the acceleration, the higher the net force, and then the higher the acceleration, the smaller the mass. Ki inversely proportional. So now our bone this part inversely proportional. Ka example, let's say for a similar situation, more a surface, and then let's say more object 10 kilograms, and then let's say more an object 50 kilograms, and then suddenly we apply a force. Let's say this is 10 newtons, and then the same here we apply a force 10 newtons. In terms of speed, this object 10 kilogram, and then this one 50 kilogram, it will the high speed, it will high. It becomes obvious about this one small mass, because this one is not heavy. This simply means the mass komunyane the high speed, and then more because the mass is greater the velocity yoba inyane. Remember acceleration key the rate of change in velocity. So the smaller the mass, the higher the velocity, and then the higher the mass, the smaller the velocity. So mass will increase, acceleration you decrease, and then mass will decrease, acceleration you increase. So that is why the acceleration is inversely proportional to the mass, because remember inversely proportional increase and then ya decrease. So this part here inversely proportional. In the exam they might ask you acceleration to increase ka factor ya bokae re increase f net or mass. Let's say for example a lekana le f net over mass. So ke nyaka tseba hore this acceleration ya go increase ka factor ya bokae this mass go increase ka factor ya 2, and then f net remain a constant. F net remain a constant re 1, and then this mass power increase ka factor ya 2 2. So it becomes obvious or increase this mass ka factor ya 2 acceleration ya decrease ka factor ya 1/2, because it is inversely proportional. It really makes sense. And then now let's see here what will happen to the acceleration re increase f net ka factor ya 4, and then this mass remain constant. So because this one remain a constant, it will be a 1. So this is a equal to 4 over 1, and then a equal to 4. It really makes sense. Re increase f net ka factor ya 4, re expect our acceleration increase ka factor ya 4. So indeed acceleration ile kana le 4. So increase the same factor ya the f net. And then now let's say increase f net ka factor ya 4, and then increase mass ka factor ya 2. So a ile kana le 4 over 2, and then e re fa gore ke 2. So acceleration ya increase ka factor ya 2. So give some of those questions on the multiple choice questions. Increase acceleration, mass, those kind of things. So what is important re increase something, whatever you remain a constant re 1, and then you increase yona re ngwala, and then wa solve whatever ba inyakao, and then re already increase ka moka, and then re la ongwala the values tja wona kaofela. So that is something very important, and that's all about this Newton's second law. And then now let's see Newton's third law. It says for every action force there is an equal and opposite reaction force. Or you can say when body A exerts a force on body B exerts the same force on body A but in opposite direction. Let's say for example two objects that are in contact. and then let's say this is body A, and then let's say this is body B. This body A, you exert a force on body B, and then this body B, you exert the same force on body A but in opposite direction. This force is 50 newtons. It means even this one you are 50 newtons but in opposite direction. Let's see real life situations, Newton's third law. Let's say this is a person. Perhaps you've seen this situation, and then let's say ulahlela a heavy object in this direction. This object in this direction, suddenly you'll realize your hand layer backwards. You apply a force on this stone or this object. This object you apply the same force but in the opposite direction. That is why suddenly you are moving in the opposite direction. And then again, let's say this is a balloon. Perhaps you've seen this situation, and then let's say this balloon is filled, and then suddenly the air blows out. What you'll realize, this balloon, you are in the opposite direction. This is because initially blow the air outside, apply this force in this direction, and then suddenly this balloon here in the opposite direction. This is because now it exerts the same force but in the opposite direction. So that is why it moves in the opposite direction. And then again, let's say this is a boat. Perhaps you've seen this situation, and then this is water. And then this person, we are in this direction, but you'll find that utswere that stick, but pusha this water backwards. But suddenly we are forward. This is because apply the force here backwards. The water I will apply the same force but in the opposite direction. That is why this person we are forward, but we apply the force here backwards. And then again, you have seen when people are swimming, swimmer o gapela metsi ko morago, but gapela metsi ko morago yena suddenly we are forward. This is because the water apply the same force but in the opposite direction. So that is why now the person we are forward. So in over some of the examples, Newton's third law, only some calculations involving this law. The next video. So anyway, that's all about this Newton's third law, and that's all about this tutorial.